Everyone, today we're going to talk about something really exciting, heat transfer. Now heat transfer is really important because I design systems, indoor coils, outdoor coils, condensers, evaporators, based on how well they transfer heat. So in order to first understand heat transfer, we need to understand three of our friends that go along with it. Conduction, convection, and radiation. Now, conduction is molecule to molecule, which I'll show you in a minute. Convection is through heat transfer, heat rises, cold falls, air flows, naturally convection, movement of heat from hot to cold. Also, radiation. Radiation is from the waveforms, the coloring from the sun. We often, when we go out in the sun, we'll get radiated and we'll actually change colors. So we'll get a suntan. Now let's take a look at these in action. I have a flame. With this flame, I got several things going on. I got radiation by the radiant waves from the different colors. I've got conduction here. I'm conducting straight to the metal, molecule to molecule. I can actually keep my hands on here for quite a while because the more massive something is, the longer it's going to take to actually heat up. So the end here is actually starting to melt. And it's getting pretty warm. But I can still keep my hands there. Now, if I take that and put it in water, behold. Now when I put it in water, I'm going to fill this up with mass. Now it's getting really hot, steam's coming at the top. It's getting too hot for me to even hold on to. Getting very hot, 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 hot. Okay, now we had both the conduction from here, then when we put it in here, we had this massive water. Filled the pipe. Now I was transferring from the pipe to the water, much more dense, and then it would convert into steam, go up the pipe, and heat the rest of the pipe right up, okay? So we had conduction, then we had convection. Now, that being said, mass, the more mass I have, the longer it's going to take to heat up. So about a nice flame like this, and I take a balloon filled full of air. What do you suppose is going to happen? Well, not very dense. Whoa. Happens pretty quick, huh? It even blew out my flame. Now if I take that same flame, add water here, water in my balloon, whoa, doesn't pop the balloon. That's because I have to heat up the water first in order to get it hot enough to melt the balloon. With air, it transferred heat very, very fast just to the plastic because the air was very expansive, a lot of area, but not a lot of mass. The water, however, has a lot of mass, so I have to actually transfer the heat into the water before this balloon will actually break. The reason for that is because everything wants to go to equilibrium. When I put my pipe in the water, it transferred the heat to the water, okay? In this room, this water is transferring its heat to the room or picking up heat, okay? It will always go to try and get equilibrium. That's why this glass of ice will eventually, if I leave it here setting long, will turn into all water, and then the temperature in this container will reach the same temperature in the room. Everything wants to go to equilibrium. With that being understood, we have convection, conduction, and radiation working on us to try and transfer heat. We have a heat transfer formula. this heat transfer formula, the two biggest things that we're going to talk about is area and delta T. However, it also talks about heat transfer coefficient, how easily the material transfers heat. One material will transfer heat better than the other. Wall thickness, the wall thickness conductivity, the area, and again, the differential temperature. So for heat transfer coefficient, we'd be talking things like the refrigerants, okay? The wall heat coefficient, we'd be talking about how well that metal transfers heat from, let's say, the refrigerant or the water inside the pipe to the outside or pulls it in. Now there are many different kinds of coils. Indoor coils, outdoor coils, evaporator, condenser, but the principles remain exactly the same. I have aluminum fins and copper tubes. I can have copper tubes and aluminum fins painted for a different color that allows me to transfer heat quicker, so color does matter. I can have steel with very few fins. I can have aluminum, all aluminum fins, all aluminum coil. I can have aluminum fins with all this prickly stuff on it, gives it more surface area. I can have microchannel coils, which has a lot of physical area, but they're physically small and light. I can have bigger coils with copper fins and aluminum, depending on my application. So if I look at these, they all have several things in common. Area and delta T. So if I take a coil like this, I'm probably going to have small physical area, so the delta T would have to be higher to transfer that heat. On something like this, I have more physical area because I have all of these extra contacts for physical area. On something like this, I'm going to have a large delta T because it doesn't have much physical area. So, heat transfer. On condenser coils, I can make them, or indoor coils, I can make these coils, whatever they happen to be, indoor coils, condenser coils, evaporator coils, condenser coils, I can make them bigger so the delta T can be smaller. They can be more efficient. I can make them smaller and the delta T will be higher, but if it's higher, then I'm going to have more lift. That system compressor is going to have to do more work. So, heat transfer. I got all different kinds of physical areas I can do, all kinds of different materials that I can use. I can change the area, I can change the delta T, I can change the type of metal, the wall thickness to affect that heat transfer. The key thing here is I want it to be a price that the customer will actually pay for. That's why we have so many different kinds. But if I'm looking for being more efficient, I probably want more physical surface area and less delta T. So, thank you very much. Heat transfer, conduction, convection, radiation, and our formulas highlight the material, how well it transfers heat, the physical amount of surface area I have to transfer heat, and if I sacrifice that, the delta T is going to go higher, which means the compressors and the things inside are going to have to work harder. That's heat transfer in a nutshell. Thank you very much. I look forward to seeing you again, or you seeing me. Tim out.